So in this lesson we're going to look at circuits, and here I have in this slide a set of what I call circuits diagram symbols. These are symbols that are common symbols that you see in circuit diagrams. Anytime you see a line, that generally relates to a wire. Anytime you see a line with dots with this weird look like a gate or a door, that's usually an open switch. I will sometimes actually close this off all the way as a closed switch. Anytime you see this squiggly line, that just means some sort of device that resists the flow of current, what we call a resistor. Anytime you see a long line and a short line, or a series of long and short lines, or a series of long and short lines with an arrow through it, that means some sort of power source. I almost always use this to talk about a power source, this end being the positive end of that battery, the negative end, positive end, negative end. I'd almost always use something like this to talk about, they say, a power pack. I'd almost use that to talk about a power supply of some kind. Anytime you see an A inside of a circle, that means an ammeter, which is a device used to measure current. Anytime you see a V inside of a circle, that means that's a voltmeter, which is a device used to measure voltage. If you ever see me use something like this, that means I mean a fuse. And then if you ever see me use a circle with some sort of squiggly line inside there, something you've probably already seen before, that's a light bulb in a circuit. So what I'm going to do first is talk about the simplest form of circuits that exist, and these are series circuits. Basically what you have in a series circuit is you have a battery or power source connected to one resistor, then connected to another resistor, then connected to another resistor, and then back to the battery. So there's just one path for charges or current to flow in this circuit, that all the current must flow in this path. There's no other place for current to go. What that means is that current must be the same in all parts of this circuit. Now, what this means in terms of voltage, if we think of voltage as the amount of energy that is given off by the battery, the total voltage of the circuit, well, that energy has to be used up in my three resistors. So the voltage drop, or the voltage in this resistor, plus the voltage in that resistor, plus the voltage in that resistor, have to add up to be the voltage of the battery, or power source. So that's my second statement. The third statement is what we would call equivalent resistance. And what equivalent resistance is it's what is a single resistor that I could replace all three of these with and have the same circuit, same current, same voltage. So basically it's a way of adding up all of these resistors or finding the sum of these resistors. In the case of a series circuit, equivalent resistance is simply the sum of the resistances of the resistors in the circuit. And you can actually show this is true by using Ohm's law. If V equals IR, so V total equals IR total equals I1 R1 plus I2 R2, and I1, I2, I3, all of those are the same, then REQ must be R1 plus R2 plus R3, so on, so on, so on. So let's do a quick example problem. Find the current and voltage in all the resistors to the circuit to the left. So a lot of times if I'm dealing with a simple series circuit, I would start with a chart that looks like this, where I have my three resistors. I'm labeling them 1, 2, and 3, and they're 20, 30, 40, and then total what happens in the circuit overall. So the first thing that I can figure out is what the equivalent resistance of the circuit is. Add those three resistors up. And so we get 90 ohms. The second thing I can do is find the total current in the circuit. What I can do here is take 20, divide by 90, and find that current. And it's worth pointing out the current is constant, so all of these values must be the same in a series circuit. So what you get is 0.222 amps in that case. What I can now do is find voltage in each of the individual resistors. 4.44, 6.66, 8.88. One check that I can do is add these three voltages together and see, do I get 20? I think you get 19.98 if you do that, which, well, I rounded this off to three significant figures. If you round 19.98 to three significant figures, you get 20. So that actually works out pretty well. So that's how we could work some simple series circuits where there's just a single path. The one thing to point out about simple series circuits is the more resistors I add, the smaller that current becomes. The way I would think of a series circuit, I usually think of it as, and we'll talk about this a little bit later, I use the airport security thought process. So think of an airport security line. You have a series of steps and each step takes a certain amount of time. If you start adding additional steps, your current flow becomes less. You can get less people through security in a given period of time because you've added more resistance to the flow through that process. Same thing would be in a series circuit. If you add more steps, more resistors, the current flow becomes less. So in the next one, we're going to look at the other type of what I would call simple circuit called the parallel circuit.